Okay, welcome once again. In this talk, we will see some MCQs related to the chapter on separable spaces, which we have studied. In the last two talks, we have seen several exercises, and before that, we have proved, we have defined several definitions. We have given several definitions of first countable space, second countable space, bare category theorem, dense set, nowhere dense set, okay, base, and so on and so forth. अच्छा अब छोड़ो, अब तो मैं सुनो, अभी मैं काट दे रहा हूँ. डोंट डिस्कस. आधा घंटे के बाद आना, आधा घंटे के बाद. ठीक है, आधा घंटे के बाद. ओके. ठीक है ये. Okay, welcome again. Now in this talk, we will see some MCQs. In the previous two talks, we have seen several exercises, and we have seen that how we can solve these exercises, what is the methodology to solve the exercises, and so on and so forth. And before that, we have discussed the dense set, the base, dense set, separable space, first countable space, second countable space, first category space, second category space, nowhere dense set, and so on and so forth. And we have also seen several examples related to these definitions, and then we have proved several characterizations for these concepts and several other results. And today in this talk, we will see separable. We will see some MCQs related to separable space, and that is to say related to the this chapter which we have discussed in the last few talks. So the first MCQ is the following: let X be a discrete metric space. Okay. Keep in your mind the definition of the discrete metric. Okay. And we have seen that in the discrete metric space, every set is open as well as closed. Okay, so let X be a discrete metric space. Then the question is, which of the following does not hold? Okay, does not hold. Now you have the collection B. Okay, B consisting all the singleton sets. Okay, so this collection consisting all singleton sets form a base for the family of all open subsets of X. So this form a base for the family of open subsets of X. So whether this statement is true or not, as I have mentioned that because this is the collection of open sets, so you can see that every open set is what? In the every singleton set or every set in the discrete metric space open, so this is your open. And so for you take any point, okay, any point, and that must belongs to this set. Say for example, you are considering a set X, then X must be in the singleton set X, and this must be a subset of an open set. So this statement is correct. The second statement is that if X is countable, then it is a second countable. Second countable means it can be written, written as a countable union of dense sets. So you have, so this is your, so this statement is also correct. If X is an uncountable, then it is first countable but not second countable. No, this is first countable. As I said, if X is uncountable, then it is first countable but not a second countable. X is countable, then it is second countable. But X is uncountable, then it is not second countable. Okay. So it means that all these three statements are holds good, but therefore the none of the above is the correct answer. So main thing is that you will have to see, you will have to remember some of the definitions, results which you have already studied in this chapter. Okay, and some MCQs, some MCQs can be followed directly from the result or from the definitions. But several things can be, you can see that if you remember the results, then you can get the answer. So this is a very important thing. And then let's take here is next MCQ. So the second MCQ is that A be a non-empty subset of X. So let A be a non-empty subset of X. Which one is not equivalent to other? Oh, very important. Which one is not equivalent to other? Means that they are equivalent, they are equivalent, they are equivalent. Each one can apply to each other. Now, we have seen that A is dense. We have seen that A is dense if the closure of A is equal to X. So this is the definition of the closure of this. And then we give the characterization that the A is dense if and only if the distance from every point X in A, X in X and A is equal to 0. So these two are equivalent. This we have already proved. Now let us see what about the C. C has non-empty intersection. A has non-empty intersection with every non-empty open subset of X. Yes, this is also true. We have proved that A has non-empty intersection with every non-empty open set. Okay, so this is proved. And the second, A has non-empty intersection with every non-empty closed sets of X. No, this is not true. So it means that this is not true, but these three are equivalent, as we have seen in a exercise, which was you can see that you can prove as an characterization. So this we have already proved in the exercise, but not the third last one. So the last is not equivalent to the rest of the three. Okay, so the answer is your D. Okay, let's take the next MCQ. The next MCQ is let X be a metric space. Okay, which of the following statement is not true? Which of the following statement is not true? A subset A of X is dense. A subset A of X is dense if and only if the complement of A has empty interior. The complement of A has empty interior. Okay, so this is true, as we have seen in the result. In one result we have proved, or we have proved this is in exercise. The second, the set of all rational numbers is dense in the usual metric space R. Yes, this is true, because we have seen this, the set of all rational numbers is dense in R with respect to the usual metric. The set of irrational numbers is dense in R with respect to the usual metric. Yes, this is also correct. The set A consisting A plus IB, where A and B are complex number, is dense. No, the set of all irrational numbers, the set of all irrational numbers is dense in the usual metric space R. So this is not correct, but this is A is equal to A plus IB is dense in the usual metric space C. Okay, C, the set of all complex numbers. This we have proved. So what we have not proved is this one. This one we have not proved. Okay, and then take another MCQ. Which of the following is true? Now here is some, you will have to go through with whatever we have learned so far, and you will have to remember something, because here you are not going to prove everything. Okay, but you must remember. For example, the question is which of the following is true. So set PAB, set of all polynomials defined on AB with real coefficient, is dense in CAB. Okay, this is dense in CAB. Second question is PAB. Okay, set of all polynomials defined on AB with rational coefficient is dense in AB. The third one is PAB, set of all polynomials defined on AB with integer coefficient is dense in AB. None of the above. So which statement is correct? So here is basically the statement is correct, is a countable dense set. So here is a little bit, if it is here is it is countable dense set. So here is it is, you can little bit modify this sentence. The set PAB of with rational coefficient is a countable dense set. Okay, so if it is countable dense, so then this, of course, this is dense. With rational, this is dense set, and with real coefficient, then this may not be countable, but here it is countable. Okay, so this statement is true, but it better you can write is a countable dense set here. Now, next exercise MCQ is let A be a non-empty subset of a metric space X, which is not equivalent to other. Okay, A is dense in X. A is dense in Z. Only open superset of A is X. No, if A is dense in X, then only superset. If A is dense in X, then only closed superset of A is X. This we have proved, not the open set. Okay, so this statement is not correct, and the only open set just joins from A is empty. This is correct. Okay, A intersects with every non-empty open set. Okay, so A intersects with every non-empty open sets, or A intersects every non-empty open set. So this is correct. Okay, this A is dense, then this is correct, and this is equivalent to this one, but the B is not equivalent to A, C and D. So the answer is your B. Answer, if only the thing is that we have proved that the A is dense if and only if the only closed superset of A is X. Okay, so just twist a little bit and then you see whether the result is true or not. So you can also, what I am saying, that you can also prepare the MCQs by your own. So all the MCQs comes from what you have studied, results, definitions and exercises. So next MCQ is the following. Let A be a subset of a metric space X. Which statement is not equivalent to other? Okay, now A is nowhere dense set in X. Then closure of A does not contain any non-empty closed set. I think this, the closure of A does not contain any non-empty open set. So then it is non-empty open set. So here it is non-empty closed set. So every non-empty open set has a non-empty open subset disjoint from closure of A. This we have proved that every non-empty open set contains a non-empty open subset disjoint from A. So we have not proved this part. Okay, if it is open here, then it is okay. Otherwise, it is not okay. So the question is, so which statement is not equivalent to other is this one. So basically, in the MCQs, you have to remember what you have studied in your subject and in your exercises, result, definitions. But here you are not going to prove everything. Okay, so this is the way. Now, the next MCQ is the following. Which of the following set is not nowhere dense set? Okay, Cantor set I have given in the exercise. Prove that the Cantor set is nowhere is nowhere dense set. Okay, so Cantor set is nowhere dense. Set of all natural numbers are with respect to the usual metric. Okay, so you can see that it's very simple. As I have mentioned, that a set of all natural numbers. So you have this n. Okay, so you have to prove this nowhere dense set the closure of interior. Okay, so closure of this is equal to R. Okay, and then you take the interior, and this is equal to R. Okay, so set of natural numbers in R with respect to the usual metric is not nowhere dense set. Is not nowhere dense set because this must be equal to empty set. So this is not a nowhere dense set. So it is a so you any subset in a discrete metric space. Okay, because any subset in a discrete metric space is closed as well as open. Okay, so you will get the interior of the set A, the closure of the set A is A, and the interior of A is A. So you will get it is equal to A. It is not equal to empty set. Okay, so you see that here is so the complement of A, where A is dense in a metric space X. So this is no. So which of the is not which of the following set is not nowhere dense set? Okay, so any subset in a discrete metric space is not nowhere dense subset. Okay, and then the next, let A be a non-empty subset of a metric space X, and A is dense in X is equivalent. A is dense in X is equivalent to say that the complement of A is nowhere dense set if A is open, A is closed, and the complement of the interior of complement of A is closed or open or whatever you can write, and none of the above. But if we have seen that the set here is the set A is dense if and only if the complement of this this we have proved. This we have proved. If A is a closed subset of X, then A is nowhere dense set in X if and only if the complement of A is dense in X. So by using this, we get the answer of this question. Okay. No, this should be answer is your the B. If A B is closed. Okay. So here is the answer is the A is closed subset of X, then A is nowhere dense set if and only if X minus A is dense. So X minus A, so but it is a reverse. No, so it is here is for this one it is different. So you can take so here is the, you can check which is the answer. And then the last one, the last MCQ is the following. It is really very interesting to see that let X be a metric space, then which of the following is possible? My question is, which of the following is possible? I am not saying which of the following is exactly true. The possible is that X has exactly 3 dense subsets. So a metric space has exactly 3 subsets. Second is X has exactly 4 dense subsets. 5 says that X has exactly 5 dense subsets. The next is X has exactly 6 dense subsets. So now the question is which one is the true? Actually, if you will see the answer of this, then you will find that so 4 is the only one that can occur among the list. Okay. So you see, a set can have many. Only the thing here is the important thing is that keep in mind a metric space can have many dense sets. Okay, not only 1, 2, 3, several dense sets can have. But here is we have to check on the possibility only. It has 3, 4, 5, 6. We are not saying that 2 or 1 or 7 or 8. We are just asking, we are just discussing whether a metric space has 3, 4, 5 or 6 dense subsets. And then you will realize that the answer is 4. So 4 is the only one that can occur among the list. So keep in mind among the list. For example, the metric space X is this one as a subspace of the usual metric space. Then X can be written is this one as a subspace of R. So that is the we have included the all these numbers. Okay, so this can be written as a subspace of R. So the possibility is the 4. So among this 3, 4, 5, 6, 4, the answer is B. There is 4 dense subsets of R. So that is the end of the MCQs related to the separable metric spaces. Okay, so I stop over here, and in the next talk we will see some exercises related to the complex set and some MCQs related to the complex sets. So thank you very much.